Hi students, in this first video for Chapter 11 and Online Lecture 21, we are now going to introduce the behavior of gases and our gas units. So what elements exist as gases? Well, we know that to be hydrogen, nitrogen, oxygen, fluorine, chlorine, and the noble gases. Remember that hydrogen, nitrogen, oxygen, fluorine, and chlorine come as diatomics, which means that they are H2, N2, O2, F2, and Cl2. Our noble gases show up as monoatomic, but they are very, very useful for us because they show us electronic stability. There are also some compounds that I want to highlight. Notice that we have the nitrogen gases of nitric acid, nitrogen dioxide, and nitrous oxide. Then we can get sulfur-containing compounds, which is sulfur dioxide and hydrogen sulfide. And then you will see that we get into the variety, but probably the best four well-known are carbon monoxide, carbon dioxide, methane, and ammonia. When we are doing problems, you will see that we are going to use these over and over and over because they are well understood examples about gaseous behavior. So what is gaseous behavior? Well, gases assume the volume and shape of their containers. This means that if you were to put in a gas into a large volume and oddly shaped container, the molecules will spread out to fill up the entirety of that container. This is going to become ever important as we get to kinetic molecular theory in our next lecture. Gases are the most compressible state of matter. This is because there is wide, large space between the molecules. For a solid, they are at an optimal distance and cannot be compressed. For a liquid, that is also true. Gases will mix evenly and completely when confined to the same container. So this means that if we have two gases and we put them in the same container, they will mix throughout the container because there's a lot of available space for those molecules to individually get the space that they are wanting. Finally, gases have lower densities than liquids and solids. We saw this back in Chapter 1 when we were talking about the units of our densities, and remember that our gases are going to have the units of gram per liter, where liquids was going to be grams per milliliter, and solids are grams per cubic centimeter. Now, this shows you that there is going to be a much larger volume for the same mass, so this means that it is going to have a lower density and helps us understand the compressibility as well as the volume and shape of containers rule that we talked about previously. Probably the most important fundamental understanding of our gases is pressure. Going back to physics, this is force over area. So what we are going to do is look at force as mass times acceleration. But the nice part about this is that we have a multitude of different units that we can describe gases with. Some of them are international, some of them are American specific, but in the end, we want to be able to describe our gases and the pressures that they exert. So as you see in the upper right, this is a typical barometer. What this is that the atmospheric pressure is going to push down on a pool of mercury, and some of that mercury is going to go up our capillary tube. For 1 atmosphere, which is our standard pressure, that mercury is going to climb to a height of 76 centimeters. But the nice part about this is that we also know that this can be 760 millimeters of mercury. So now we also have to look at what that means about us for our atmospheric pressure. Notice at sea level, we are going to give the standard of 1 atmosphere. If we go 4 miles into the air, notice that our pressure has been reduced by half. And if we go 10 miles into the atmosphere, we end up getting a pressure of 0.2 atmospheres, or about 20%. Why is this important? Well, if we think about this, at 4 miles, that is approximately 21,000 feet. This is the approximate altitude of a jet airliner. So the reason that our jet airliners fly at the altitude they do is that we're trying to reduce the air resistance, which then gives the plane better mileage, and it should be cheaper on their expenditure of gas. So it's really important that as you understand, standing here on Earth, you have a large column of air pushing down on you every moment of the day. The higher in altitude you go, the less you're going to have pushing on you. So let's talk about our units. The Pascal used to be our SI specific unit. The reason why is you will see the kilogram, the meter, and the second, all SI derived units. So 1 Pascal is equal to 1 kilogram meter times second squared. However, most of the calculations we do is going to use another unit. So 1 Pascal is actually 1 Newton meter squared. You will notice that this directly coincides with our idea of our force over area. The SI unit for force is the Newton, and our area is going to be meter squared. But we very much like to use the atmosphere. The atmosphere is going to be the standard unit that we use for all of our equations in this chapter. 1 atmosphere is equal to our 760 millimeters of mercury, as well as the torr. The torr is another unit that is equivalent to the millimeter of mercury, and it comes from the physicist Torricelli. Now we can state that 1 atmosphere is equal to 101,325 pascals, or in many cases, we will talk about it as 101.3 kilopascals. We are going to use this conversion many times over because of the correlation between atmospheres and ultimately the kilogram and the joule. The atmosphere is also equal to 29.92 inches of mercury. This is taking our 760 and going and dividing it by 10 to give us 76 centimeters that we saw before, and then dividing by 2.54 that we saw back in our conversions chapter. This is beneficial when you are watching the Weather Channel and they are talking about the atmospheric pressure because they will historically talk about it in inches of mercury. Finally, we can go to the PSI, which is pounds per square inch. This is the unit that you will typically use when inflating bike tires, car tires. Notice that 1 atmosphere is 14.7 PSI. So as you're filling up your car tire and you're trying to fill it to approximately 30 to 35 PSI, notice that you are just over 2 atmospheres of pressure. And finally, the last one we are going to talk about is the bar. 1 atmosphere is equal to 1.013 bars. You can see that that also comes from the kilopascal and is just a unit conversion. So let's try a couple of examples. The pressure of an industrial propane tank is 935,000 pascals. What is this pressure in millimeters of mercury? So the first thing that we want to do is go and write our original unit. So that is 935,000 pascals. Now, it's important that you use the atmosphere as your intermediate unit for our cancellation. It can be very difficult to remember exactly how many pascals there are in millimeters of mercury, but we can always go to atmospheres and have one extra step. So now what I can say is that 1 atmosphere is over 101,325 pascals. And now that I have atmospheres, I am able to go to millimeters of mercury. So that is 760 millimeters of mercury for 1 atmosphere. And you will now see that my pascals shall cancel, my atmospheres, and I'm left with millimeters of mercury, which is what I want. And I will get a value of 7,013. So with correct sig figs, I should say that I get 7,010 millimeters of mercury. So as you can see, it's very important to be able to convert from one to another. And as you'll see in many of the problems in this chapter, I might start with non-standard units, such as millimeters of mercury, bars, PSI. You should be able to convert from one to another, and you really want to be able to get to atmospheres. For our second example, a typical scuba tank has a pressure of 3,000 PSI. Convert that pressure to torr. So let us do the same procedure that we did a moment ago, and that is saying that we have 3,000 PSI, and it's best for us to go to our atmosphere. So for our 1 atmosphere, if we have PSI, remember that is 14.7 PSI. So now we would have atmospheres. We don't want to just stay at atmospheres. We want to go to torr. Remember that the torr has the same numeric value as the millimeters of mercury. So that would be 760 torr for 1 atmosphere. So I'm able to cancel out my PSI, my atmospheres, and I am left with torr. If I do that, you should get a value of 155,100 torr. If I go and do my scientific notation, that should be 1.55 times 10 to the 5th torr. And you will see that by my answer selections, that should be answer E. Converting from our units are incredibly important because you're going to see a multitude of them during this chapter. So finally, let's talk about how we study different pressures. We are not going to use the barometer like many of our Weather Channel folks. We're going to use what is called a manometer. A manometer is a laboratory gas measuring apparatus for us to understand our pressures. There are 2 types. So the first one we want to look at is the closed tube. Notice that the closed tube name comes from this end right here. We are going to trap a small amount of space in a vacuum between our mercury and our closed tube. When we open up our valve, our gas is going to pour into our manometer and begin to push against our mercury. Normally, the mercury at a resting state would have an equal height. So we are going to mark that equal height with 2 red lines. But then notice that as the gas pours in, it will push the mercury up around the bend and into our vacuum space. The pressure of our gas is equal to the height of our mercury and doing the conversion from centimeters of mercury or millimeters of mercury. This is how you would measure gases in the lab. Now, the hard part about a closed tube is that we actually have the difficulty of going and making the closed tube and trapping the vacuum. It's slightly more expensive. A different way of doing this is what we call an open tube. Notice that we have an open tube here on the right side. So if we started with our same resting mercury, as our gas is going and pushing in, you will notice that our mercury goes around the bend and up to gain its elevation. But the problem with this is that you actually have another gas pushing against the mercury on the other side. Our atmosphere is going to be pushing against this side. So what we know about this is that our pressure of the gas not only has to deal with the calculation of the height using our millimeters of mercury, we must also know the atmospheric pressure as well, because the gas is fighting against the mercury as well as the atmosphere. This does not happen in the closed tube. In this video, you saw the importance of not only the characteristics of the gas, our units of our gas, but also how we are going to study gas behavior and create the fundamental laws that you're about to see in the next video. Have a great day.